regarding the evening sessions. So if you haven't been to the Arizona Winter School before, we have evening working sessions starting at 7:30 at the hotel. So it's the same place where the reception was last night. And so the working sessions are designed for, well, the one thing for the project groups with the speakers. A lot of students are working together with the speakers on various problems. We'll have a chance to present their findings on the final day of the conference, so on Wednesday. But everyone is certainly encouraged and welcome to attend the working sessions. In fact, lots of people come and discuss mathematics and refreshments. It's quite a lot of fun. You get a lot of work done, and certainly everyone is involved. I do want to say for students who are on projects, one thing you might want to do today during one of the coffee breaks is to get together with introduce yourself to the speaker you're working with, and so that everyone can start to know each other. And so tonight, sort of. Okay, so in any case, I want to introduce our next speaker, which is Benedetto of Morse College.
So thank you for the invitation. Thank you all for actually showing up. Let me get right to this. Joe has previewed some of this talk a little bit. So let me just start by hopefully just reviewing some basic things about non-Archimedean fields. So K will denote a field with a non-Archimedean absolute value. That is to say a real value function with the following properties. It's always non-negative, hitting zero if and only if you actually plug in the zero field. It's multiplicative, and it satisfies not just the triangle inequality, but the stronger non-Archimedean triangle inequality that the sum of two things is never bigger than either one of them. By the way, there is a thing called the trivial absolute value, which just sends absolutely everything, declares everything to have absolute value 1 except 0, which of course has to have absolute value 0. I'll always assume we're dealing with a non-trivial absolute value. So 0 always has absolute value 0, 1 always has absolute value 1, but there'll be something else that has some other absolute value. And usually I'll assume that my field is complete with respect to the absolute value. So all Cauchy sequences converge. And what I mean by with respect to the absolute value is the definition of Cauchy and the definition of converge both involve an absolute value somewhere, so use this absolute value. So one of the cute things about, and useful things about non-Archimedean fields is that a series converges in a complete non-Archimedean field. A series converges if and only if the terms go to 0. So all of our calculus students have really been thinking they're working in non-Archimedean fields. Okay, so also any non-Archimedean field comes with several useful features. For one thing, if you look at the closed unit disk, so OK is what it's often called, set of all things of absolute value less than or equal to 1, that is a ring. It's closed under addition, because if you add two things of absolute value less than or equal to 1, it can't get bigger, so it's still less than or equal to 1. It's closed under addition, it's closed under multiplication. It's a ring. And it has a unique maximal ideal, namely the open unit disk, set of all stuff of absolute value strictly less than 1. And it's easy to check that that is indeed a maximal ideal and unique. So since it's maximal then, if you take the quotient, you get a field, which is often called the residue field. And it's a useful property of the original field. So for example, one of the things you can look at is the characteristic of the two fields. The original field, capital K, is characteristic, and the residue field, little k. So if the original field had characteristic 0, then the residue field could have either characteristic 0 or positive characteristic. But if the original field is a positive characteristic, then the residue field has that same positive characteristic. Easy to verify. Another thing that arises is the value group, although I guess different people probably call it different things, but it's just simply the set of all those positive real numbers that are actually absolute values of things. That may be the entire positive real line, but it usually is not. It's usually some proper subset of that, but it's certainly a subgroup because it's multiplicative. Okay, great. This is the picture to have in your mind when you talk about a non-Archimedean field geometrically, or this is a picture to have in mind. So I've drawn an attempt to, and you can't actually draw these things. These are non-Euclidean, you can't actually fit them into R2 or R3 or anything, but this is an attempt at giving you a pictorial idea of what a non-Archimedean field, in this case with residue field is the field with 3 elements, and which is discretely valued in the sense that this this value group here is a discrete subgroup of 0 to infinity. In which case there is an element, I'm calling it pi here, so you see these little pi's floating around. So pi is a uniformizer. That is, it is an element of the field which has absolute value strictly less than 1, but maximally so. So there's there are no absolute values attained between absolute value pi and absolute value 1. So in that case, what I've drawn here is I've simply drawn, this is okay here, is this disk, medium-sized disk here, is the ring of integers, the set of everything of absolute value less than or equal to 1. I didn't call it nk here, but this pi ok is the maximal ID for this slightly smaller disk right here. And what's going on, the fact that the residue field has 3 elements is just simply observing, well, here I've added 1 to that maximal ideal, here I've added 2 to it. These are different cosets of the ideal. And if you added 3 to it, I guess you would end up back here, although it's possibly moved around. So you're seeing the fact that the residue field has 3 elements and that there are 3 of these disks sitting inside the original disk that I started. And by the way, there's nothing in these gaps of air over here. There's nothing there. And then of course, once you've got this disk with the 3 disks inside it, there's also, that's just using the additive structure, there's also the multiplicative structure, so we can multiply by pi, that gives us this disk, and each of these disks here has been multiplied by pi, so that gives us these 3 smaller disks in here. So I've labeled one of them as pi squared times okay. And within each of those we have 3 smaller disks, and so on down. It continues down forever. It looks, in the end, or okay at least, in the end, looks essentially like a Cantor set on 3 intervals instead of 2. Yes, I know a Cantor set on 3 intervals instead of 2 is homomorphic to Cantor set on 2 intervals, but if you don't know that obscure little fact, that might be misleading. It's easier to just think of it, in this case, as a Cantor set on 3 intervals. I haven't actually, one of the problems with the sketch is I haven't actually drawn any points that are actually in the field here. I mean, any point of this field is you imagine these sequence of circles heading downward forever, and a point is the final intersection of all these disks all the way down. And that's the only thing in the set. And then, of course, you can divide by pi as well. So I've intentionally tried to draw this to look like it's continuing onward, this big, really big disk around here would be pi inverse times the ring of integers, within which you have 3 of these disks that are the same size as OK was. And then you can multiply by pi to the -2, which gives you something even bigger. So it's like a Cantor set that's now growing up towards infinity as well. And that's the whole field, is something like that. So within that, you have this ring of integers, and then you have this field which is more infinite inside. Okay, so that's the picture you should generally have in your mind when you're talking about a non-archimedean field, something like that. And in particular, you can just see by how many of these next size disks down there are in there, you can see what the residue field is. It appears geometric. All right, but I'm also going to not be happy with just a field like that. So if you want to take extension fields, in particular an algebraic extension of the original field, and I'm sorry, if you have a complete non-archimedean field and you take an algebraic extension, then the absolute value extends uniquely to that extension. I don't want to talk about how it can be done. By the way, if you have a non-complete non-Archimedean field, the absolute value does extend, but that extension may not be unique. Let's not worry about that. The new residue field is automatically an algebraic extension of the old one, and this is very easy to see. The new value group certainly contains the old value group as a subgroup, so you may pick up some new absolute values along the way. The way you should view that back in this picture here, if I take a field extension of this original field, capital K, you might pick up some more disks here. So here I have the residue field is F3. Maybe the extension field, the residue field is F9. So instead of having 3 disks here, I have 9 disks everywhere. And maybe now there's more absolute values attained, so now maybe I can pick up the square root of pi, so that would give me sort of more layers to my onion. And if you, I said this is true for any algebraic extension, well, you can do it for the algebraic closure in particular, which is going to give you the algebraic closure. Its residue field will automatically be the algebraic closure of the original residue field, and the new value group will be much bigger in general. In particular, the algebraic, even though K was complete, the algebraic closure is generally not going to be complete. So you go to the algebraic closure, you lose that. So then you can complete, because you do have an absolute value, you can take the completion of the algebraic closure. That thing is often called C sub k, and mercifully it is still algebraically closed after you complete, so you don't have to continue alternating these operations of algebraic closure and completeness forever. It does stop. And this C sub k is the thing that we're normally going to be working over in my lectures. Okay, so let's give hopefully familiar example of the p-adic numbers. So pick your favorite prime, and you can put p-adic absolute value on rational numbers by just, well, given any rational number, well, any non-zero rational number here, I guess, you can write it as some quotient r over s, where r and s are integers with no p's in their prime expansion, and times some positive or negative or zero power of p. And the p-adic absolute value of that is, we'll just take the reciprocal of the p part. So in other words, if you're divisible by a large power of p, you're small, and if your denominator is divisible by a large power of p, you're big. So it's just a different absolute value to put on the rational numbers. It's easy to check that it is in fact a non-archimedean absolute value, and you can complete with respect to that. And the completion, the way I like to think about the structure, the one I think most people think about the structure of the completion, QP, the field of p-adic rational numbers. Think of it sort of as the set of all, for lack of a better word, Laurent series in the variable p. So it's a formal Laurent series where the coefficients are all in the set from 0 through p minus 1. Or to put it another way, it's base p expansions, except you're allowed to now extend infinitely far to high powers of p. Not infinitely far to negative powers of p. So you have to start somewhere, but then go arbitrarily high powers of p from that. And that starting point could be negative. So like I said, it's sort of like Laurent series. Except, unlike formal Laurent series, when you add and multiply these guys, there's carrying. So it really is like adding and multiplying base p expansions as you go. Again, I hope this is familiar, and most of you have messed around with p at some point. Within that, the ring of integers is often, instead of being denoted O sub qp, is usually just denoted v sub p, and it's the set of all, continuing the Laurent series analogy, it is the set of all power series with coefficients, again, in the set 0 through p minus 1. The maximal ideal is the set of all those power series with no constant term. So just everything p times something in zp. So when you take the quotient of that, zp by the maximal ideal, you're basically just picking up the constant term, which is something from 0 through p minus 1. So the residue field is fp, the field of p elements. And also the value group, it's not too hard to see. Oh, I guess I didn't say it clearly, but this absolute value extends in a canonical way to qp. And the value group that you pick up is just integer powers of p, positive or negative integer powers of p. Again, I hope that's familiar. What may be a little less familiar, but hopefully you've seen it, is if you take the completion of an algebraic closure of qp. So as I suggested on the previous slide, the residue field of that is now going to be the algebraic closure of fp. And the value group is now going to be, instead of all integer powers of p, it's going to be all rational powers of p. And I hope it's clear that it should be at least all rational powers of p, because, I mean, for example, p was an element of qp that has absolute value 1 over p. Well, the square root of p is supposed to be an element of the algebraic closure, and that's going to have value 1 over the square root of p. So p to the negative half power. And similarly, any fractional power of p should pick up. But you're not going to pick up anything else. So the key thing I want to point out here is, first of all, the residue field of this CP thing is now infinite because it's algebraically closed. And although the original value group was discrete, that's a discrete subgroup of the positive real line, the value group of CP is, while it's not all of the intervals 0 to infinity, it is dense. And this is, both of these points are going to be important later. Okay. Another example, so the previous example was something coming out of when you look at number fields. If you look at function fields, you're led to Laurent and then more generally Puiseux series. So you learn about formal Laurent series when we do, undergraduate algebra. So fix your favorite field, capital F, you can talk about the field of all formal Laurent series, which now we are truly adding and multiplying as formal Laurent series, no carrying or anything like that. It has non-archimedean absolute value. What I mean by order at t equals 0 of f, I just mean the order of the 0 at f, or equivalently, if you're talking about a pole, it would be the negative of the order of the pole. So fix your favorite real number epsilon between 0 and 1, say 1/2, for example, and just take 1/2 raised to the power of the order of 0. So if you have a formal Laurent series that that doesn't actually start until the t to the 10th term, then the absolute value is 1/2 to the 10th. So it's very small. On the other hand, if you had a pole there and it starts with the negative 10th power, then your absolute value would be 2 to the 10th, which is relatively large. So if you have a pole, you're big. If you have a 0, you're small. And again, it's easy to check that that's a non-Archimedean absolute value and that the Laurent series field is complete with respect to that. The ring of integers, I hope not surprisingly, is the ring of now power series as opposed to Laurent series, so no poles allowed. And the maximal ideal is power series lacking a constant term. So just take t and multiply it by a power series. The residue field, again, you're taking power series modulo power series lacking a constant term, you just get back a constant term. So in other words, you get back the original field that you started with. And the value group is just all integer powers of epsilon. Again, I want to talk about the completion of an algebraic closure of this thing. It's often called the field of formal Puiseux series over F. So it'll involve series not just in the variable t, but also in any fractional power of t is allowed to show up now. I'm sorry, what did I say?
You want to get through this series.
Oh, yeah, okay, sure. But, I know, that's why I put it over F. So I'm trying to general. Maybe I should say formal generalized Puiseux series. So yes, technically Puiseux series refers to characteristic 0. But I'm running the talk. And the residue field is now going to be the algebraic closure of the original residue field. And the value group, again, is now not just integer powers, but rational powers of the whatever epsilon that you chose. Okay, great. All right, so hopefully most of what I've just been talking about is essentially review with maybe a few little new things sprinkled in. Now I'm going to start to shift gears towards things that are maybe a little less review-y. Well, disks, I guess, are still pretty much review. You can do this in any metric space. In particular, a value field is a metric space. You have a metric given by the distance from A to B. It's just the absolute value of A minus B. So you can define the open disk of radius r centered at a point A of your field to be the set of all points in the field that are distance less than r from A, and the closed disk is less than or equal to. Please note, by the way, even if I'm working over a field K, my disks are always going to be in CK. So I'm always going to be talking about, when I talk about this notation for the disks, I'm always referring to a subset of CK, not of K. You can, of course, talk about disks in K, but I don't want to do that. I'm also specifying that my radii are always positive. They can't be zero. All right, so please note, if R is not actually in the value group, if R is not actually the absolute value of anything, then the open disk and the closed disk of that radius coincide. And in that case, we call that disk an irrational disk. That's sort of motivated by, in the previous slides, the value group was given by something raised to all rational powers, so this is something that's not a rational power of that generator. So that's where the name comes from. Of course, if R is actually the absolute value of something, then the two disks are actually different because there will be stuff that has absolute value equal to R, so these conditions will actually differ from one another. And in that case, we call the open disks a rational open disk and the closed disk a rational closed disk. I mean, you can just talk about an open disk or a closed disk as well, but sometimes we want to give this finer level of specification. There is an very important technical thing to keep in mind, though, however. In spite of the names open disk and closed disk, as topological sets, that is, so this is a metric space, you have a topology that induced on it. As topological sets, all disks are both open and closed as topological sets. By the way, you can see that from, I don't want to go back to all the many slides to get back to it, but from that picture of my sketch of a non-Archimedean field. Maybe I will go back to it. Pardon me? Yeah. Have you seen this talk before? If you go back to this, I mean, you can see, for example, I mean, here's the closed unit disk. The open unit disk is substantially smaller than the closed unit disk. I mean, and that's because there is no boundary. The thing you want to call the boundary, the stuff of absolute value 1, is not some thin little set. It's a fixed set. It's got all this stuff. And in fact, I'm working over CK, so actually there's infinitely many of these disks. So, right, CK has infinite residue field. So what you should try to be picturing in your mind here is I've only drawn 3 of them, but there's actually infinitely many of these disks running around. So the open disk is just this little thing here. The stuff of absolute value 1 is infinitely many of the same size disks running around in there. So in particular, the closed disk is an open set. Similarly, an open disk is a closed set. All right. In addition, in spite of what I just said, though, even though topologically all disks are both open and closed, there is a difference. There's a true distinction between those that are rational open, those that are rational closed, and those that are irrational. So yes, they're all open and closed as topological sets, but as disks, there's a true difference between irrational, rational open, and rational closed. You can only, any disk is exactly one of the 3 things. To make things more confusing, because of the non-Archimedean triangle inequality, any point of a given disk is just as good a center as any other point. So if you pick your favorite open disk of radius r centered in A, and pick any point you want in that open disk, any point B in that open disk, then the original disk is also the disk of radius r centered in B. It's the same disk. This is very easy to check from the non-Archimedean absolute value. Same thing for closed disks. So centers are not well defined, but because I'm working over CK and because the value group of CK is dense, the radii, however, the radius of a given disk is a well-defined quantity. In fact, it coincides with the metric space diameter of the disk used as set in the metric space. Again, these things are fairly easy to prove. Oh, Joe commented in his lecture that he wasn't going to prove much. He referred you to his lecture notes. I'm not going to prove anything. And refer you to my lecture notes where I try to prove these things pretty thoroughly. All right. Just for today, I'm not going to prove anything ever. So let me just point. Well, maybe I'll prove this. If you believe what I've just said, that any point of a disk in the center, it follows the 2 disks intersect if and only if one contains the other. Because the picture you have, if you work over the complex plane, is, here's one disk, here's another disk. If they intersect, that's what they intersect at some point. That's what sort of the intersection of 2 disks look like. Well, if you're working over a non-Archimedean field, that never happens. Because if you have, say you had that situation, 2 disks intersecting, well, any point of a disk is a center. So actually, the picture doesn't look like what I just drew. That point that I just drew is the center of both of the disks. So really, the picture looks like that. So whichever one has the larger radius contains the other. This feels very weird if you've never played with this before, but it's because the space is highly non-Euclidean, and it doesn't look like our usual picture. It's easier actually once you get the idea. I heard somebody mutter earlier, all non-Archimedean fields are totally disconnected. I guess this isn't really directly about disks, but it's because of disks. This is because of the fact that all disks are both open and closed as topological spaces, as topological subsets. It follows immediately that it's not too hard to show that any non-Archimedean field is totally disconnected. What that means is the only connected subsets are, well, the empty set and singleton sets. And as soon as you have at least 2 points, you're automatically disconnected. You sort of fall apart in dust. And again, a non-Archimedean field looks kind of like the Cantor set. It's sort of geometrically, that's sort of what it looks like. All right. Just a topological point. QP and the ring of the field of Laurent series over a finite field, these are locally compact non-Archimedean fields. But whenever you take the algebraic closure, you're not locally compact. In fact, I hope I'm saying this right. A non-Archimedean field is locally compact if and only if 3 things. Its residue field is finite, its value group is discrete, and it's complete. If any one of those 3 things fails, the field is not going to be locally. And by the way, it's also a non-Archimedean field is locally compact if and only if its ring of integers is compact. I don't really want to talk about that much. The main thing you should take away from this is the bottom line, or from this point in here, is that CK is not locally compact. That's the main point of that last little bit. Okay. So we're going to ultimately be doing dynamics here. So I want to tell you about what polynomials do to disks. Now, to preface this, let me point out, if you take a disk in the complex plane, take a closed unit disk, in the complex point, or the open unit disk, and you hit it with a polynomial. So take your favorite polynomial, don't make it something easy like z squared, take some crazy polynomial with 7 non-zero terms, and apply every point of the stick the closed unit disk into it. Look at the image of that under the closed unit disk, under this crazy polynomial. You're going to get some weird set. I guess it'll be connected, but it's going to be a mess. It's going to be twisted all around. So this is what happens to non-archimedean. So let's take a disk, so specify a center and a radius. And here's a polynomial, which I've intentionally rewritten so that it's sort of its expansion is centered at point A. It's the center of my disk. More generally, I could take actually a power series with coefficients in my field that's centered at the point A, although I need to assume some mild convergence conditions, which are laid out in full in my lecture notes. And what I'm going to do is I'm going to define S to be this other radius, this maximum right here. By the way, the mild convergence conditions here essentially say that this maximum is defined. That is that it is attained, so there actually is some n for which absolute value Cn r of the n is the maximum, but for a polynomial, of course, that's clear that there's only finitely many terms you're looking at for a polynomial, so clearly this thing makes sense. So that's some real number, and if the polynomial is non-zero, then that's some, if the polynomial is non-constant, then that's a positive real number. By the way, please note, this is the maximum where n bigger or equal to 1, so I'm ignoring the constant term when I use. And I set I to be the minimum integer for which, that is attained. The minimum n for where this quantity hits the maximum, and j to be the maximum integer for which it's attained. Of course, it's very possible that I could equal j, but maybe not. Well, it turns out that the image of the corresponding disk, either open or closed, under G, is a disk. It's not some crazy twisted thing, it's a disk. It doesn't have any holes in it, it's just a disk. Okay, so non-archimedean fields are really much easier than complexes, as our calculus students knew. So, and in fact, not only that, but the open disk maps I to 1. By the way, the image of the disk is certainly going to contain this constant term, C0, right? Because A maps to C0. So it's going to be a disk centered at C0, and its radius is going to be exactly this quantity S, right here. And it's going to map I to 1, so the open disk will map this number I to 1 onto the open disk, and the closed disk will map this number J to 1 onto that closed disk. Counting multiplicity. Of course, there could be critical points in there which map with some multiplicity to their image. But if you look at any point in the image disk, any point here has exactly I images here counted with appropriate multiplicity. This is proven in the lecture notes, but I do not even want to come close to touching this today. But this is a very important fact. Everything you do in p-adic dynamics, you need to know this fact. So, but let me just, in lieu of a proof, let me just demonstrate an example of this. So here's a polynomial defined over the p-adic field. Perfectly good thing right there. And I'm going to look at this centered, I think I decided on this centered at 0. So let's look at the image of, and just so that the slide is not huge, I'm going to stick only to closed disks, but you can imagine the same thing for open disks. Let's look at the image of the closed disk of radius r, centered at 0. Well, according to the previous slide, it's going to be some disk centered at the constant term of some radius s. The constant term here is p cubed. So it's going to be a disk centered at p cubed of some radius s, where s is, right, that looks like a mess, but this is actually very simple. So what's going to happen is initially, when r is very small, this term right here, the p, so ignore the constant term, of the non-constant terms, the pz term here is dominant if r is very small. I mean, what the previous slide is saying is just look at whichever term has the largest absolute value, and that's the one that sort of controls it. So if r is very small, then these guys here, you're raising r to high powers, so they're going to be very, very small. So of these 4 higher power terms, pz term is going to be the biggest. Its absolute value will be absolute value of p times r, or in other words, 1 over p times r. And that will happen up to this absolute value until you hit absolute value of p itself, which is the point at which these two terms, the square term and the linear term, tie for biggest. At that point, the square term takes over as biggest. And then the square term dominates, and so the image radius is just the absolute value of the square term, which is to say r squared, from where we left off before up until you get to this crazy absolute value, which if you check is the absolute value at which the square term and the 5th power term tie for biggest. please note that the cube term here is actually a red herring. He is never big enough to actually be the biggest ever. So that he is never the maximum for any value. And so then from this point onward, for all radii bigger than that, the fifth power term is just bigger than everything. And so you end up with the image radius. It is the absolute value of this term. It's the absolute value of p to the fourth times r to the fifth. Does this make sense? I mean, I'm just explaining what the rest of the previous slide says. By the way, a little side comment, of course, since disks can be centered at any point of the disk, as soon as S gets large enough that 0 is actually in the disk of radius p cubed, disk radius S centered at p cubed, you may as well call it the disk centered at 0, right? Again, as soon as the point's in the disk, you may as well call it the center. So if you prefer the image disk to be centered at 0, you can do that once S gets to be up to p cubed. Or equivalently, if R gets up to size absolute value of p squared. Also, as far as the degree of the mapping, when the degree 1 term was dominant, the mapping was 1 to 1. When the degree 2 term was dominant, the mapping is 2 to 1. And when the degree 5 term is dominant, the mapping is 5 to 1. So, again, this is just summarizing what the previous slide says for this particular example. But as Joe said, we don't really want to work on CK or C. We want to work on the projective line. So the projective line over CK, again, is just staple in a point of infinity. Again, this is an official algebraic geometric way to do this, but let's just think of it adding a point of infinity. And I will define a P1 disk to be either a disk in the usual sense, or, well, I also need to have a notion of what it means to have a disk containing this new point of infinity. And for that, it turns out the correct notion is just simply take the complement of an old disk. So everything outside an old disk. And you can call these disks rational open, rational closed, or irrational in the obvious way. It always annoyed me in grad school when professors would say something was obvious, so let me say what I mean by the obvious way. So if what I'm talking about here is a disk in the old way, a subset of the old CK that happens to be this, I just mean rational open, rational closed, or irrational. Before, if I mean a complement of a disk, the complement of a rational open disk is defined to be rational closed. The complement of rational closed is defined to be rational open. And the complement of irrational is irrational. All right. So this is the cool theorem, which is really just sort of the generalization of the thing on the couple slides previous. If you take a disk and hit it with a rational function, take a P1 disk and hit it with a rational function, you might get all of P1. That is to say, you might have the image of a disk under a rational function might be the entire P1 of CK. But if that doesn't happen, then the image is a P1 disk. So there's no crazy bending or twisting, or there's no way to get, like, say, all of P1 with a single point removed. Take a disk and hit it with a rational function, you get a disk. Or you get all of P1. And that's really just a fairly straightforward corollary of the theorem on the previous slide, or a few slides back, appropriately stated. All right, but disks aren't enough. So more generally, I want to talk about these things called connected aphanoids. So a connected aphanoid is simply a non-empty intersection of finitely many P1 disks. Or probably the way to think about it better is take a disk, more generally a P1 disk, and punch finitely many disks out of it. So for example, an annulus, one disk with a smaller disk removed. But you might have 7 smaller disks removed. So, so some circular piece of Swiss cheese, basically, something like that. By the way, one thing to worry about here, it's called a connected aphanoid. Remember, however, CK is totally disconnected space, as is P1 of CK. So in spite of the name, a connected aphanoid is not connected as a topological set. Okay, again, look, it's got this Cantor setting kind of feel to it, but that's what it's called. Just rephrasing what I just said here. Sorry, I forgot to mention. Again, you can call these things rational open, rational closed, or irrational, or maybe none of the above. So a connected aphanoid is rational open if it is the intersection of finitely many rational open P1 disks. It's rational closed if it's the intersection of finitely many rational closed P1 disks. It might be none of the above. Like if you took a rational open P1 disk and intersected it with some rational closed P1 disk, then let's just connect that. Oh, by the way, anyone out here who's a fan of rigid analysis is probably fuming at me right now because in true rigid analysis, one would only call a rational closed connected aphenoid a connected aphenoid. But I'm not a purist, so I'm going to call it this. My definition of connected aphenoid is a little bit more general than what rigid analysts would say. All right, so the reason these guys are called connected aphenoids, or one of the many reasons they're called connected aphenoids, is that they behave like connected sets even though they're not connected sets. In particular, if you take the image of a connected aphenoid under a rational function, again, just like with disks, you get either all of P1 or you get a connected aphenoid. So yes, it's not technically a connected set, but in your universe of rational functions, it behaves like a connected set. It's not going to get ripped apart by a rational function. And that's one of the justifications for the use of the term connected to describe connected aphenoid. It's too much to ask that the inverse image of a connected aphenoid be a connected aphenoid, because nothing like that even happens for the complex plane. If you take the inverse image of a disk in the complex plane under a rational function, you expect to get a bunch of disjoint sets. And that's what happens here. You get the inverse image of a connected aphenoid is a disjoint union of finitely many connected aphenoids, each of the same type. If the original connected aphenoid was, say, rational open, then each of these new guys is also rational open. And each one of these guys maps di to 1 onto the original aphenoid in such a way that the sum of the terms is d. It has to be because, oh yeah, I said degree d. I said degree d here. This is the same degree as Joe was talking about, maximum degree of numerator and denominator, which is the number of pre-images that any given point has. So this degree, it better be d, because every point in U has exactly d pre-images under the rational functions. Okay, great. So the point is, connected aphenoids behave very nicely, both under forward and backwards images of rational functions.
For a power series, you have like an infinite number. For the restricted power series,
You have an infinite number of what?
yeah.
Oh, no. So there, yes, in theory, if you had so what I in the notes called a restricted power series, those are sort of rigged up so that you have only finite infinity, actually. But if you had a power series that simply converges on, say, the open unit disk, as opposed to being a restricted power series in the open unit disk, the preimage of some subdisk could be infinitely disks. Yes. But there's a notion of restricted power series which actually ends up having a well-defined degree, in which case, for those guys, you don't get it. But that leads to some very complicated questions involving these fancy things called analytic elements, and I don't go there. Homie only plays with rational functions. So, all right. So here's, let me just give you an example of this. So here's a perfectly nice polynomial. Again, I'm going to work over the p-ax, but a similar sort of thing happens over any non-Archimedean field. Let's take U to be this following connected aphenoid. So this is a rational closed connected aphenoid. It's the closed unit disk with the open unit disk removed. And again, this is an open set. It's not just some thin little circle. It's got all these big, thick circles, disks within it. You can check, this is not obvious, but you can check with a good little exercise if you get confused during a future talk. Check that the image of this thing is the full closed unit disk. So you hit every point in the closed unit disk when you apply this polynomial to this thing, and you hit nothing else. Although there's one funny thing that happens here. So by the way, this is just illustrating the first point of this theorem. The image of a connected aphenoid is again a connected aphenoid. It's a single disk. Although in this case you don't necessarily get nice full d to 1 mapping. So actually some of the points in the closed unit disk have only one pre-image in this angles, and some of them have two. So it's not, for the forward image, you might not get this nice d to 1 mapping. If you look at the reason that's happening actually is that if you look at the inverse image of this closed unit disk under the same polynomial, you don't just get this annulus, you get actually the whole closed unit disk maps onto it. And that's why some of these points were mapping 1 to 1, others mapping 2 to 1, because there were some of the points that one of the times they were supposed to get hit was by points in the open unit disk that we removed. So So it turns out that the closed unit disk maps 2 to 1 onto the closed unit disk. And then there's also, I should sketch this. So what's happening is, here's the closed unit disk. And that's mapping to itself 2 to 1. And then out here there's this smaller disk centered at 1 over p, I guess. And it's of radius only absolute value of p, which is smaller than 1, and that maps onto the closed unit disk 1 to 1. It turned out. Again, this is not obvious. I don't expect you to see this just looking at this, but it's not too hard to just pen and paper compute. You might need the back of 2 envelopes instead of 1. It's pretty straightforward. Yeah, so this is what I was just saying about the degrees. So the closed unit disk in this case maps onto itself 2 to 1 to you, and this other smaller disk off to the side maps 1 to 1. And just to show you, if you take an even bigger disk, so I looked at the inverse image of the closed unit disk, and I look at the inverse image of this closed disk with larger radius. Please note this absolute value here, this is bigger than 1. P has absolute value smaller than 1, so this is large. This is P cubed here in absolute value. Its inverse image is just a single disk that maps 3 to 1 onto it. So again, this is all just to illustrate the theorem on the previous slide. All right, that's a polynomial. Let me show you an example of a rational function here. So this is a relatively simple rational function, just z minus 1 over z. This is a rational function of degree 2. As you can see, when you write it as a single fraction, the maximum degree of the numerator and denominator is 2. And indeed, every point in the entire P1 will have exactly 2 preimages, counting multiplicity. If you look at the inverse image of the open unit disk, it turns out that it is the disjoint union of 2 other open unit disks. So again, this is illustrating that slide from before. The inverse image of an aphanoid is a union of finitely many aphanoids of the same type, connected aphanoids of the same type. Well, hang on, I said it's 2, its inverse is the disjoint union of 2 disks. Well, that's if the residue characteristic is not 2. Because if the residue characteristic is 2, then the distance from 1 to minus 1, well, it might not be 0. The distance from 1 to minus 1 will be 0 if we're actually characteristic 2. If we're in residue characteristic 2, which is a weaker claim, then that only says that the absolute value of 2 is less than 1, not necessarily actually 0. So, but in any case, if the residue characteristic is 2, then those 2 disks coincide. So if we're not in residue characteristic 2, then each of those 2 disks, the disk of radius 1 centered at 1, and the other disk centered at minus 1, each of them maps 1 to 1 with the open unit disk. If we're in residue characteristic 2, however, that's the same disk, and it maps 2 to 1 onto the open unit disk. Again, you can just check this simplifying. Start looking for strikes. Just start trying to solve the equation z minus 1 over z equals c, where c has absolute value less than 1. You just play with that and see what the inverse images look like. However, if we look at, instead of the inverse image of the open unit disk, if we look at the inverse image of the closed unit disk, then we actually don't get a disk anymore. We get a connected aphanoid. We get an annulus, in this case, the closed unit disk minus the open unit disk. Again, you can check this by hand. And that annulus maps 2 to 1 onto the original disk. This is part of the reason why I needed to introduce connected aphanoids. Because even if I really cared about disks, when I started looking at inverse images, even just of disks, connected aphanoids come up, as they have right here. I look at the inverse image of this disk, and it was not a disk anymore. It was connected aphanoid. But that's as bad as it gets, because inverse images of connected aphanoids are finite unions anyhow. Connected aphanoids. Okay, so hopefully that explains why I brought these obnoxious beasts into the disks. I hope we're reasonably happy with disks. Well, actually, if you want to be happy with disks, you need to be happy with connected aphanoids as well. But they're not bad. They're just intersections of disks. They're finite intersections. Okay. All right. So finally, we get to dynamics. And now that we've sort of done some warm-up p-adic or non-archimedean analysis. So fix a rational function. Again, as Joe said, always of degree at least 2. Joe essentially defined these terms. It's exactly the same definitions as before. You have a periodic point of exact or minimal period n. I guess again, as Joe did, assuming for the moment it's not infinity, you define lambda to be its multiplier. That is the derivative of phi to the n, the first iterate that lands it back on itself. Take the derivative of that. So that's an element of ck. That's the multiplier of the point, of the periodic point. And as Joe said, if the point is if infinity is periodic and we want to know its multiplier, just make a change of coordinates move it away from infinity and compute the multiplier that way. It's not going to affect the multiplier. And you say that the point is, again, attracting if its absolute value less than 1, repelling bigger than 1, indifferent if it's equal to 1. Of course, this is now the non-archimedean absolute value. This is not the complex absolute value anymore. But you can say all those words. And they do sort of mean what they said before. If you near an attracting periodic point, stuff gets sucked in. Near a repelling periodic point, stuff gets pushed away. A little less clear maybe what happens in a different periodic point. Just a side note, so if you take a different point in the periodic cycle, like say you have a point of period 3, so A maps to B, maps to C, maps back to A, you can compute the multiplier of the point A, so take the 5 to the 5 composed of 5 composed of 5, take the root of that at A, that gives you some multiplier, or take it at B, or take it at C. Well, you're going to get the exact same multiplier at all three. That's an easy exercise in the chain rule. And another easy exercise in the chain rule is multiplier is independent of what coordinate you're in. So if you make a change of coordinates, that is conjugate the function. The periodic point is moved, but its multiplier is not changed. Okay. Now, Joe mentioned that there's this spherical or chordal metric on the Riemann sphere. He didn't give the precise formula for it, but it basically looks like this, except we have, instead of like an L infinity looking norm, there would be like an L2 looking norm. So the max would be the square root of the sum of the square root of it. So anyhow, when you're working in the non-Archimedean, everything is always L infinity, not L2 when you work in the non-Archimedean world. You always take maxes and stuff when you're doing things non-Archimedean. So anyhow, it turns out this is the appropriate formula for what's spherical metric, an analog of the spherical metric. So this is, the idea is here, I guess we're not really embedding this in some larger space like you think of the Riemann sphere being embedded in R3. I'm not thinking about it that way. This is just its own thing. But it conveys the same idea that if you have a point of very large absolute value, or let's say 2 points of very large absolute value that are close to each other, so you really sort of view the thing as wrapped up as like a sphere with the point of infinity to the north pole. I guess technically what I wrote down isn't defined at the point of infinity, so really you should write it in homogeneous coordinates to indicate that, but don't write that down. Think about that. I'm not going to let you write it down. There it goes. So, all right, but now we get to Fatou and Julia sets. So this is where the main meat of the subject really starts to arise. So the Fatou set, as Joe said, is the set of points in P1 of CK now, for which the family of iterates is equicontinuous. That is to say, on a neighborhood. So I'm getting around Joe's thing about the largest open set by just saying I want the thing to be equicontinuous in an entire neighborhood. So it's equivalent to what Joe said. And again, intuitively, that means that it's a set of points at which anytime you have another point that's close to it, so delta here is the spherical metric, close to the spherical metric, you take any iterate of it, the resulting two iterates are also close to each other in the spherical metric. I'll give a different definition though in a second, so that's why I'm waving my hands a little bit here. And the Julia set is defined to be its complement. Now, by the way, you'll notice the words classical here. That's because in a future lecture, I'm going to give a different definition of a different set, so I want to distinguish them. And again, the idea is that in the Fatou set, if you mismeasured your initial point, you have a small error, it's not going to matter as you iterate the thing, that small error stays small, but if your point was in the Julia set, an initial mismeasurement could become an enormous mismeasurement later. Okay, essentially by definition, the Fatou set is open, the Julia set is closed. As Joe mentioned, the Fatou set of an iterate is the same as that of the original function. He said that was easy. In one direction, that is really easy. One inclusion is really easy. The other direction takes a little more work, but yes, it's not that hard. They're also invariant under the function. So if you take a point in the Fatou set, its image and all of its pre-images are also Fatou, ditto for the Julia set. The attracting periodic points because they suck things in are Fatou. The repelling ones because they push things away are Julia. Here's that equivalent definition, at least for CK, and you can do something like this over C as well. So what this says is a point is in the Fatou set if and only if you can find a P1 disk containing it, such that if you look at the union of all of the iterates of that disk, it misses at least 2 points of the non-Archimedean sphere. So this is not obvious that this is the same, but it turns out to be true. And in practice, this is what you always use. If you want to show something from the Fatou set, what you do is you find a disk where the union of all the iterates of that disk is easy to understand. If you want to show something in Julia, you show that no matter how small a disk you take, you essentially cover everything. So this is the definition that's used in practice. All right, so here's just an example of these two things in a minute or so. So if you take this quadratic polynomial, if the absolute value of a here is less than or equal to 1, it's not too hard to see the closed unit disk maps into itself using the non-archimedean absolute value. Sticking anything of absolute value 1 into that, everything inside is absolute value equals 1, so you get out something of absolute value equals 1. Well, that means the union of all the iterates of the closed unit disk are contained in the closed unit disk and omits certainly at least 2 points of the sphere. And so that's the 2. And similarly, the complement of the closed unit disk also lands inside itself. And so if you look at the union of all the iterates of that P1 disk that is the complement of the closed unit disk, that's also misses most 2 points. So the point is that the 2 set is everything, and the Julia set is empty. So Joe hinted at this, that in the non-Archimedean world, it is possible, in fact, very, very easy, to get the Julia set to be empty. A little bit more interestingly, if the absolute value of A is somewhere strictly bigger than 1, you can take the disk containing, so take this disk U0, which is of radius R, so it's a fairly big disk. If you look, it's not too hard to see everything outside of it. The complement of that disk gets mapped off to infinity. It's contained in itself. So that disk, everything in it, complement of U0, everything in it is the 2. What I can do is now I can define U1 to be the preimage of U0. It turns out what you get is 2 smaller disks here. So U1 is the disjoint union of those 2 little disks that I just stepped in. And if you take the inverse image of that, it's 4 even smaller disks. And if you take the inverse image of that, it's 8 little tiny even smaller disks. And so on down. And if you keep doing this, what you get is a Cantor set. And that's what turns out to be what the Julia set is. So you get this Cantor set. The complement of it, the Fatou set, everything in the Fatou set eventually, under enough iteration, leaves U0 and then gets sucked off to infinity. And so the Julia set is this Cantor set. It is, in fact, homeomorphic to the Cantor set in this case. And the Fatou set is everything else. An acute example, Nigel Smart and Chris Woodcock showed